In this mini tutorial, we will look at RMS and how it relates to voltage and power. RMS stands for the root mean square, and as the name suggests, we calculate the RMS value of a waveform by squaring it, taking the average, and then square rooting the final result. This will become more apparent after we derive the equation. The RMS is used to quantify the amount of voltage or current needed to supply an equal amount of energy to a load in a given time, regardless of whether it's an AC waveform or a DC waveform. This basically means that an RMS AC voltage will deliver the same energy to a load as a DC voltage over a given time period. If the time period is variable, then it means that the average power delivered to the load over that time period is equal, be it an AC supply or a DC supply. I've got two example circuits drawn here, one supplying a DC voltage to a resistance, and another one supplying an AC voltage to a resistance. If I draw the voltage waveform over time, that's T against V, for the DC setup, it will look like a straight line, horizontally, because the voltage is not changing with time. At the same time, if there's a voltage being dropped across the resistor and a current flowing, then there must be a power, so I will also draw in another time plot, but this time against power. And just like with the voltage, if the voltage is not changing, then the power is also not changing over time. So again, it looks like a horizontal line. Although they look the same, the power is actually of a different level to the voltage, because the formula for power is current times voltage. So even though I have drawn them looking alike, you'll see that there's no actual numbers on the vertical scale. If the power is being dissipated in the resistor over a certain time period, which we will label as some arbitrary value of T, capital T, which is the typical symbol for a time period of some amount, then there will be a certain amount of energy which is dissipated in that resistor over that time period. The amount of energy, which in this case we'll call E for energy, which is dissipated in that resistance over a time period T, is obtained by integrating the power waveform. So energy is equal to the integral from 0 to T of the power, which is this waveform here, over time, dt. And that effectively gives us the area underneath the curve here. So underneath the power waveform, we have basically we've quantified the area underneath that power waveform. If I now replace the DC voltage supply with an AC voltage supply, for a start, when I draw my time axis, V is now going to be V as a function of T, because it's time varying. If I give it a peak value equal to this one, so whatever this voltage here is, which I can call VDC, if I make the peak value of my AC waveform, which I will draw in, equal to that amount, so V peak is equal to VDC, and this will result in a power waveform, the same as what we had before. So I draw P. This time is also a function of time, but the power waveform will look like this. Badly drawn, but basically it will look like that. The power being delivered to the load will be equal to the power being dissipated in the DC scenario only at the peak. Because we made the peak voltage equal to the DC voltage, then the power dissipation in the load in the AC system will be equal to that in the DC system at the peaks only. So at this point here, the P AC is equal to P DC, if we call this one here P DC. The rest of the time, the power is lower than this amount, which means that less power over a time period of T, if this is T again, is being delivered to the load. It also means that if I integrate this waveform in the same way as I did to quantify the energy, I get the area under the curve again, which is this area. We can see that there are areas here where no energy or less energy is being dissipated. So whereas before we had a solid rectangle over a time period t with a maximum height of pdc, now we have this sine squared function, but there are gaps in it. So if the height at the peak is equal to pdc and the time period is equal to t, just like before, then you can see that where there was energy being dissipated before, there's now not energy being dissipated. So the amount of energy dissipated into the AC load must be less than that of the DC load if the DC supply is replaced with an AC supply. It also means then that if I want to deliver the same amount of energy to a load over a given time period, then the peak value of the power, and hence the peak value of the voltage, must be higher than the DC value. But how much higher? And that's where the RMS comes in. Firstly, we can quantify crudely what we've done by using some examples. So if I put some example figures in for the DC scenario, and we'll let the voltage be 12 volts, we'll let the time period be 1 second, we'll give a resistance of 10 ohms, that will give us a current given by Ohm's law, V over R, which is 1.2 amps, and then there will also be a power, which is given by the current times by the voltage, which comes out to be 14.4 watts in this scenario. The energy being dissipated in the resistance then is given by the integral from 0 to our time period t of our power waveform dt, and because the power waveform in the DC system isn't changing with time, then that can simplify down to simply just the power, DC power, times the capital T, and that comes out at 14.4 joules, the same as the power, because our T, capital T, is 1 second. If I now switch to the AC example, again we'll have a peak voltage of, we make our peak voltage equal to the DC voltage, which was 12 volts, but because the voltage is time varying, then we need to know what the function for our time varying voltage is. So in this case it's a sine wave with a peak amplitude of 12 volts, so it will be given by 12 times the sine of omega t. Again we will make our capital T 1 second, and our resistance will be 10 ohms. So exactly the same setup as before, the only difference being that the voltage is now AC. There's a current with a peak value, of 1.2 amps, because it becomes equal to what it was in the DC scenario only at the peak, which means that the time varying current will follow the same function as the voltage, so it will be a sine wave with a peak of 1.2 amps. And the peak power, P peak, will be the product of the peak current and the peak voltage. And that comes out at 14.4 watts only at the peak. The time varying version of the power, P of T, is going to be the product of the time varying voltage and the time varying current. And that's going to come out to be a sine squared function because we're taking the product of two sine functions, and that will be 14.4 as a peak times sine squared omega t. And if we then want to calculate the energy that has been dissipated in the resistor over this time period, capital T, we integrate that power waveform, P of T, and that will bring us out a value. If you do the sums, that comes out at 7.2 watts, which you can see is not equal, beg pardon, sorry, that's not watts, that's joules. It's not the same as what we got in the DC supply. So even though the peak voltage of our sine wave is equal to the DC voltage, because of the fact that as we progress in time, where before there was energy being dissipated in the load, there is now no energy being dissipated. There are areas where the energy dissipation is less or even zero, then the amount of energy dissipated over the equal time period, capital T, because they are both, we're sampling over the same time period, is less. So we get 14.4 joules there and 7.22 joules there, and the rest is contained in these missing areas. So this is where we quantify the RMS. Ohm's law states that V is equal to I times R, and I is equal to V divided by R. And that can be substituted into the power equation to eliminate the current or the voltage and give power purely as a function of voltage and resistance or as current and resistance. So if I substitute either of those into my P equals I times V equation, then I get the power is equal to V squared divided by R, or it's equal to I squared times R. So for a given resistance, I can then work out the power by just using either the voltage on its own or the current on its own. These values scale linearly for any fixed value of resistor, so as long as the resistance isn't also a time-varying parameter, then I can simply just say that the power is proportional to the square of the voltage and is also proportional to the square of the current. So now if I quantify the energy being dissipated in a load, I do as I did before, which was the integral from 0 to our time period of our power waveform dt. But now I can replace power with either the voltage squared or the current squared. So I do that, and I get the integral from 0 to t of v of t, remembering that it's a time varying parameter, so I put this t function in there, squared dt. If we remember back to our previous slide just a moment, that we had to work out, to give the energy is this area contained inside here. What we've basically done is we've got a rectangle with a height and a width. The width is the time component and the height is the power component, but it is the average power component. If this was, this is a DC level, but if it had ripples on it, then we would basically take the average of that to make it a straight line. So make it a static value, which we can then multiply by our horizontal value, and it'll give us this area. So I could also, I could modify this value to say that it's equal to the average power times the horizontal component, which is capital T in this case. If we now come back here, I can say that this E is equal to the average power times the horizontal component of capital T, just like we did here. So if I now rearrange that and I want to get the average power, I know that the average power is equal to the energy divided by the time. And we know that by using the units as well, because power is in watts, energy is in joules, and time is in seconds, and watts is equal to joules per second. So we know that that works. And that is all equal to the energy, which is given by the integral from 0 to t of v of t squared now, dt. That's the energy, and to turn it into an average, we divide the energy by the period, and so there's our equation for average power. But of course, power, again, is proportional to v squared. So we could also say that the average power is equal to the average voltage squared. And then finally, we bring the square over, because we don't want volts squared, which is power, we want volts. So to get the volts back from the power, we simply unsquare it, and that gives us the average power, which is given by this equation, and we take the square root of the whole thing. And this equation here is the RMS, equation. So that gives us the RMS voltage, because we have taken the voltage waveform, we've squared it, we've taken the average of it, or the mean, and then we've square rooted it. So it's the root of the mean of the square. RMS. Now, before, we needed to know what peak voltage are we going to need in order to dissipate the same energy over a time period as a DC voltage would do. We know it's not the peak here. We can't set the peak equal to the DC because that gives us this scenario, which we worked out, gives us a much lower power or energy dissipation over a time period. So we need to find out what is the peak value required of a given sinusoidal or time varying waveform to give us the same power dissipation or same energy dissipation as with a DC value. And so we can take what we've got. So we know that our V of t in a DC scenario, I should say, if we take our DC scenario again, we've got a voltage that's not varying over time, even though I've given it a time varying, because even though it's not time varying, we are still considering it as a variable over time. And that was 12 volts static. We have a period of 1 second, and we have a resistance of 10 ohms. The RMS voltage we can get from this because we simply say that the RMS, using our newly derived equation from here, is given by 1 over t times the integral from 0 to capital T of V of t squared dt, and we take the square root of the whole thing. And that, because the voltage is a static value of 12 volts, is going to come out at 12 volts. So then the power is going to be the RMS voltage squared divided by the resistance, and that's going to come out at 14.4 watts, because it's 12 squared divided by 10. And that's exactly the same as what we had in the previous example. 14.4 watts is what we got. So that's fine. Now if we look at the AC scenario, we want to find out how many volts peak do we need to put in order to get our equal energy. So we need to dissipate 14.4 watts average over a time period of T, capital T, or 14.4 joules over that same time period needs to be delivered. So we start off with our voltage function. Voltage as a function of time is equal to some peak voltage times by the sine of omega t. Now we need to find our peak voltage. We know that the energy dissipated that we want is 14.4 joules. That's what we want to dissipate in order to make the AC system the same as the DC system. Because our T here, we've got a T of 1 second, so even though I've only gone as far as the power here, we know that the energy in this DC system is also going to be 14.4 joules, because it's just the power times by the time, which is 1. So that's what we want. That becomes our requirement. So again, we'd say that power in watts is equal to our energy in joules divided by our time in seconds, and that equals 14.4 watts. And that is going to be equal to the RMS voltage squared over our resistance, which is what we've just set up here. And so if we substitute our RMS voltage in, we have 1 over t times the integral from 0 to t of V peak squared times the sine squared omega t. Notice that I've squared it because this here is basically the integral from 0 to t of V peak sine omega t, all squared. So that's why I've squared it. Now if we look over back to our drawing that we made before of our power waveform, the sine squared function looks like this. So if we ignore the v peak section for a moment and just concentrate on the sine omega t, which has an amplitude of 1 by default, so just if we just look at the sine squared omega t component by itself, that is a waveform that looks like this but has an amplitude of 1. And if that has an amplitude of 1, if I take the average of that, if I then take this waveform and I integrate it over a time period and then divide out that time period, I've got the average power, P average. And that, if this is 1, it's going to equal a half, because it averages to, over time, it will average to half of the peak amplitude, because it's a symmetrical waveform about 0.5. Even though I haven't drawn it as a symmetrical waveform, it is in fact. If you go and plot a sine squared function, it will come out as a symmetrical waveform between 0 and a maximum amplitude of 1, and the average comes out as a half. So with that in mind, I can now take this section, so not the v peak, in fact I can bring the v peak outside because it's a constant, and then take the average of the sine squared omega t dt. I forgot to put my dt on there. And that bit here all comes out to a half. So now my final equation is that my power is equal to v peak squared over 2r. And then I can simply work out my v peak. V peak is equal to 2 times p times r, take the square root. And if I work that out, I substitute in 14.4 watts for there, and I substitute in 10 ohms for that, the answer comes out at 16.97 volts. And so I will need to put a sine wave, if I'm using a sine wave, I will need to give it a peak amplitude of 16.97 volts in order to dissipate the same energy in that resistor over a time period, capital T, as I did when I just had a DC voltage of 12 volts. If the peak of the sine wave is 16.97 volts, then the RMS of that waveform is 12. So what does all this tell us? It tells us that if I apply a DC voltage to a load, and it dissipates a certain amount of energy in a given time period, then if I swap the DC voltage with an AC voltage, then it's not the peak that I have to make equal to the DC voltage, I have to make the RMS equal to the DC voltage. So in order for an AC voltage and a DC voltage to dissipate the same energy in a load over a time period T, then their RMS values must be the same, not the peak and not the average. It just so happens that the RMS and the average are the same when you're dealing with a DC voltage because the value is constant. But in a time-varying one like a sine wave or any other time-varying wave shape, the RMS and the average may not be the same, especially if the waveform is bipolar, meaning it has a negative cycle or half cycle. So the RMS voltages must be the same in order to dissipate the same energy in a time period. And that is the crux of the matter when we're dealing with RMS. That is why RMS is important. There is a shortcut to determine the RMS voltage or current from a sinusoidal waveform, but it only applies to a sinusoidal waveform, as I will now demonstrate. If I take a sinusoidal waveform in the time axis there, and we have, say, volts going up, and I draw in a sinusoidal waveform like so, then the power associated with that is obviously the square of the voltage, which gives us an associated power waveform, which is going to look like that. And if the peak amplitude of the sine squared wave is 1, then the average of it over a time period is going to become a half, as we saw before. If yeah, and this is our period again, 0 to t. So the peak lines up with the peak. The peak, because it's squared, all negatives become positive, so the trough and the peak line up, and the 0 lines up with the 0. So this has the function sine omega t. This has the function sine squared omega t. And it's all scaled by some peak value. So this would be v peak, and this is v peak squared. Squared. So if I want to work out the RMS voltage, I use our formula again, this one, the one that we derived before, and we say that the RMS is equal to 1 over t times the integral from 0 to t of v of t squared dt. And we take the square root of the whole thing. We start off with our formula that we've worked. I will then take the square root over the other side, so I don't have to keep writing it down every time. So I square both sides, and we end up with 1 over t times the integral of v t squared dt. I can then substitute in for v of t our function, which is this. V of t is a amplitude times the sine of omega t. So we put that in. So it's 1 over t times the integral from 0 to t of v peak times the sine of omega t all squared. Which of course, if I take my square inside, then becomes v peak squared times the sine squared of omega t dt. So we're now dealing with this waveform. We've squared the voltage, and we've given us a new waveform, which is the sine squared. We're on this one now. And the average of it is a half. So keep that in mind, because my v peak is not a time varying parameter, it's a constant, so I can take it outside. So I have my v peak, and then I multiply that by our averaging function, dt, and of course all of this collapses to 1/2. So I can finally say that my RMS voltage is equal to v peak, Mr. Squared off there, v peak squared over 2. And the Mr. Squared off there. So the RMS voltage squared is equal to v peak squared over root 2. So I then square root both sides to get the RMS voltage back. And that is just simply equal to v peak squared over 2 all square rooted, which finally simplifies to v peak over root 2. So I can use this little equation here to work out the RMS of a sinusoidal signal. If I know the peak voltage, then I simply divide it by root 2, and that will give me the RMS. As well as that, I can also flip that over and say that if I know the RMS and I want to find the peak, I just multiply the RMS. I multiply the RMS voltage here by the square root of 2, and it'll give me the peak voltage. So that is a shortcut which will allow you to that allows you to work out the RMS of a sine wave only. You can't use that for a non-sinusoidal waveform. It'll only work on a pure sine wave because the square of that sine wave looks like this, and the average comes out to 1/2. And this whole thing here, as you see, assumes that the square of the sine wave function collapses to 1/2. If this is not a sine wave, then this is not 1/2, and this whole assumption breaks down. So you may still get an approximate value using this, but the more and more distorted your sine wave becomes, then the less accurate the answer from this function will give you. And I will demonstrate that using the simulation. These waveforms show the voltage and current from an AC system. The voltage is the green waveform, and you can see that that is a nice sinusoid. The current is the blue waveform, and it's quite distorted. The voltage has a peak of 12 volts. So if I simply take 12 volts and divide it by the square root of 2, which is 2 to the power of a half, I get 8.485. And if I look at the RMS as measured in the simulation, I get 8.485, you can see. So the answers agree. If I now look at the current waveform, which is distorted, it's not a sinusoid. If I was to do the same method again, first off looking at the peak is about 356 milliamps, so 0.356 amps, 0.356, and I divide that by the square root of 2, or 2 to the power of a half, I get 0.251, or 251 milliamps. If I now look in the simulation and see what the measurement says, you see that the answers do not agree. It's lower. It's a lower value, not what I just calculated using the shortcut. And the reason for that is because the shortcut assumes that the waveform, being purely sinusoidal, occupies all of the area underneath this curve. So if there's a peak of some amount, then all of this area underneath it has to be filled under the waveform. Here, with the blue waveform, that's not the case. You can see that there's a peak here, but only one half of it is filled. The other half is cut off. And as you see, the answer has come out approximately half of what we calculated. I calculated 251, and I got 162, which is approximately half of what the answer should have been. And that's because of this missing section. Finally, we come to the most important part for your coursework, which is to discrete time sample an AC waveform and determine the RMS value. So we start off with our equation again, that the V RMS is 1 over t times integral from 0 to t v of t squared dt, and we take the square root of the whole thing. This integral works in the continuous time domain. So you use it to analyze a continuous time waveform. In the continuous time domain, we assume that the sampling period, which is this little dt here, is infinitely small, which means that we are basically taking the sum of an infinite amount of samples. Now, we can't sit here and work out an infinite amount of samples longhand. So what we do is we move to the discrete time domain. So V RMS in the discrete time domain becomes 1 over n times a summation of n equals 1 to n of V of n squared. And then we take the square root of all of that. This is the discrete time domain, and here the sampling period is a finite amount, and we assume that it's the same between all samples, just like in the integral, but we have a finite number of samples now, whereas before we had an infinite number of samples. Because we have a finite number of samples, instead of integrating over a time period, we're now integrating over a number of samples, which is capital N. And if we have a data set of samples, we take each one, square them, add them all up, divide them by the number of samples we have, and then take the square root of the final result. If I have a waveform, a simple AC waveform, I can sample it at discrete time intervals, and to make the maths nice and easy, I will sample it 8 times. So we have our first sample, which is 0, 1 at 0.5, 1 at 1. This is assuming that the sine wave has a 1 volt peak amplitude. We have 0.5 again, 0, minus 0.5, minus 1, minus 0.5 again, and then we're back to 0. So the overall, before it repeats, we have taken 8 samples, 1, 2, 3, 4, 5, 6, 7, 8, before the waveform repeated, so our capital N is 8. So we have a data set 0, 0.5, 1, 0.5, 0, minus 0.5, minus 1, minus 0.5. Those are our 8 data points. And to work out the RMS of this, we simply plug it into our equation, this discrete time sampled version of it. So we are adding them all up, so we do 0 squared plus 0.5 squared plus 1 squared plus 0.5 squared plus 0 squared plus minus 0.5 squared plus minus 1 squared plus minus 0.5 squared. We divide all of that by our capital N, which is 8, and then we take the square root of the whole sum. We can simplify that down, because 0.5 squared, that's a half squared, is a quarter. So we effectively have a quarter, 0 disappears, plus 1 squared is 1, plus a quarter again, plus 0 disappears, plus minus 0.5 squared becomes plus a quarter, plus minus 1 squared is 1 again, plus another quarter. And then all of that is divided by 8 and then square rooted. So that becomes the square root of 3 over 8, which is equal to 0.612. And this is our RMS voltage of that waveform. Now, it's a bit crude. Because it's a sine wave, the real RMS voltage, as we determined earlier, should be in the region of 0.7, 0.707 area. But mine's come out slightly low because my sampling period is very low. I've taken a very small number of samples, which means that the value I get is going to be quite crude. But if you increase the number of samples, you should get a much more accurate value, one that's much closer to the real amount.